Welcome back to ECE 442-542. This is the first segment inside Lecture 6.1 that's not an announcement segment, and this one is going to be talking about or summarizing the PID controller and what they represent or how they might be used or how they're useful in designing controllers. And the first thing that you might take note of, I've been saying PID, I keep saying PID and not PID. Please, if you're in an interview or if you're somewhere else and they start talking about controllers, you probably don't want to say, oh yeah, we designed a PID controller in 542 or in 442. If you do, just don't let them know who your instructor was, please. Anyway, PID controllers, that's PID is standing for proportional integral derivative. And you may not want to always be saying proportional integral derivative controller, and that's why it's been given the acronym PID. So let's now look at this controller structure. It's a particular structure, and let's just talk a little bit about the concept. PID really says that you're working with the air signal. Here the closed loop diagram is illustrating the fact that the reference input is being directly compared. There's no filtering action happening between the measurement of the output signal and it being compared with the reference input. This is unity negative output feedback configuration. We now have three different ways that we can influence the air. We could influence it by scaling it proportionally, and that's maybe you could think of that then as this proportional component of the total input that's going to adjust or drive the system. And in some cases, maybe that's all we need. Maybe we do not need integral action. Maybe we do not need derivative action. But in general, we have all three of these pieces and they are in parallel. We now have the integral action, U sub I. So the piece of the total input that is responsible for integrating this air signal and using that to influence the input to the plant. And then we have our derivative component, U sub D. We now have three different components associated with this PID controller, and to talk about it, let's just illustrate this with continuous time signals, but just realize that we are going to be using these PID controllers in a digital control setting. The proportional control, you can see that here. K sub P, it's just scaling linearly the air signal and using that to produce this U sub P, the top component in this three-part input that makes up the total input driving the plant. And you can now see that the air at the present time is just being scaled by this proportional gain K sub P, and that is what is referred to then as the proportional term or the proportional piece of our controller. That's the P piece. It's the works with the air signal at the present time. The integral term, U sub I, is now actually integrating. And look at what it's doing. It's now taking the air, but it's taking not just the current value of the air, it's actually integrating from wherever we began in time, minus infinity, up to the present time, t. We're integrating that entire air signal, and using that, we're weighting that by another gain factor, K sub I, and that then produces the integral term in our PID controller. The integral term then, if the proportional term deals with the present time, the integral term deals with the past air signal. And that's represented by going from minus infinity, integrating all the way up to t, the present time. Contrast that with the derivative term. And these obviously are very representative of how they are described. Proportional, we're just proportionally scaling the air. Integral, we're integrating the air. Derivative, now we're actually differentiating the air at the present time. And what's that doing? That's giving us a slope. That's telling us where are we anticipating going. This derivative term works with future air movement. It's trying to anticipate in what direction is the air going. Then we are going to scale this term with a gain k sub d in response to the air or the direction of the air. Where are we headed? And that's dealing with future. So you can see that now we are looking at designing a controller that works with sort of three different time histories or time intervals of the air. The present time is the proportional, previous time is the integral, and future time is the derivative. And let me sort of illustrate that with this picture. Let's just assume that our air signal decreases with time, and that's what we would hope in a well-controlled system. We would like, if this is now a closed loop system, remember what that air signal is doing. The air signal is really just saying, oh, what's the difference between where we want to go, our reference, and where we are actually at, our output y. We're comparing that through this summing junction. That produces the air signal, and that now is what we hope to make smaller. We want the present output to eventually go and become equal to, usually, the reference input. So we would anticipate this air signal going to 0 or at least getting smaller, and that's what I've indicated with this blue curve. I've now drawn a line in the sand. T sub 0 is the present time. I'm saying that is now. What happened in the past precedes T sub 0, and that air and the area underneath that air, that's what happens to the integral of the air signal. That's what the integral component of the PID controller is doing. The proportional term is working at the instantaneous value of the air, and what we are seeing when we calculate the derivative of that air, we now know that, oh, we're going down. We're using that information in the derivative piece and the future time. So when you think PID controller, you can think of these three different time intervals that you're concerned with. Previous or past, that's dealt with the integral portion. The present time, or the now, that's the proportional gained part of the PID controller. And the future, or what you're anticipating is happening to the air, that's how the derivative term enters into the PID controller action. And in fact, control is always usually concerned with this trade-off between steady state accuracy, which is really going to be enhanced by the integral term in the PID controller. The transient is influenced obviously now by the derivative. How are we moving? What are we anticipating? And the proportional piece. The proportional piece is at the current time, but this trade-off we usually now are wanting to, we have to, based on our insight of the given system and how we want it to behave, we're usually trading off Steady state accuracy, oh, we can really reduce the error, but we're going to have to allow a larger overshoot in our transient behavior. Or somebody might say, no, I cannot tolerate any more overshoot, but I can sort of accept a larger steady state error. Maybe the output can be within a centimeter of the reference input, depending on what you're controlling. If that's now some large vehicle, maybe that's acceptable. Maybe it is not, but that's what you're going to have to do now with many control scenarios, is you're going to have to make this decision. How do I trade off steady state accuracy with speed of response? What's going to help you with that decision is the design of this PID controller.